Hello, still on our AC sizing. So in our last session we computed for the lighting load, the equipment load and the occupant load. Now the next step is to compute for the conduction through our building envelope, the walls, the windows, the roof and the door. So let's get on with it. I think we can copy this aspect or cut this aspect rather. Alright, so as I said earlier, this is the heat transfer coefficient for the conduction through our building envelope, and here are the definitions I explained in our last session, if I remember correctly. So now let's compute for change in temperature, and our change in temperature is T out minus T in, outside temperature minus the indoor temperature. The outside temperature, we are assuming that this project is going to be done in Abuja. Abuja is a temperate region, most especially in the month of March. So I think it's safe to assume 36 degrees Celsius as our outside temperature, while 24 degrees Celsius should be our desired indoor temperature, a comfortable temperature. We don't want the space to be too cold so as not to affect the productivity of users. Alright, having said that, now let's convert our temperatures, which are in degrees Celsius, to Kelvin. You will see why we are converting them to Kelvin. We are doing it to make our units consistent. I believe we all recall converting degrees Celsius to Kelvin means you add the temperature to 273.15, right? And that will give us three oh 9.15 Kelvin. The same thing goes for our desired indoor temperature of 24 degrees Celsius. 87.15. So all right, so now our change in temperature now is T out minus T in, which will now be 309.15 Kelvin minus 297.15 Kelvin so we have 12 Kelvin. Now the reason we are converting this to Kelvin is our U factors, that is the coefficient of heat transfer of our materials having Kelvin in their units. So in order to make the units consistent so as to get accurate result, that's why we are converting our temperatures to Kelvin. Now let's start with the walls. We already have our wall area, so I think we can just I don't think we need this part since we've already computed for wall area. Net wall area 87.5 meters squared. Alright, so now wall U factor, remember our architect did not furnish us with the wall schedule, so we are just going to assume that the wall is a common wall which we normally use, that is a 230 mm hollow block with 20 mm plastering or rendering on both sides, that is the outside, the external and the internal. We don't know the kind of paint the architect is proposing. We don't know if it's a heat resistant paint, because a heat resistant paint can reduce the conduction of the wall significantly, but since we don't know, in order not to undersize, we are just going to assume high. So let's assume 2.0 watt per meter squared Kelvin as the U factor for our wall. So you can see the unit, watt per meter squared Kelvin. So that is why we converted our temperature to Kelvin. So now we have our wall area, we have our U factor, we have our change in temperature, which is 12 Kelvin. So we just go ahead and put all this into the formula. I'm just putting the units so that it will be very clear. So we are having 2100 watts. That is for our wall conduction. Now for the windows, we don't know the kind of material the architect is proposing. Why? Because we don't have the schedule for the windows as well. Let me show you what I mean. So you can see this is a typical architectural drawing. This is the elevation, one of the elevations, and this here is the door schedule. This here is the window schedule. So you can see this type of window. The window this architect is proposing is anodized aluminium, 5 mm thick clear glass casement windows fixed at the top and bottom to anodized aluminium thick clear glass fixed windows. So this is a thick clear glass, maybe a double glazing glass. So you can see this is a window schedule. So in our own case, as usual, we have to assume, since we don't have these details, like I said, the right course of action is to contact the architect so as to know the kind of material. But for the purpose of this training, we are just going to assume. So let's assume it's an ordinary glass. We have various types of glass. We have a reflective glass, which is very good in resisting heat. Why? Because it reflects a reasonable percentage of the heat instead of conducting it. So we have a reflective glass, we have a double glazing glass, we have a single glazed glass but tinted, we have an ordinary clear glass single glazed. So let's assume in our own case that this is a clear glass, and let's assume 3.0 to be the U factor for this glass. So now again, as usual, we'll just use this formula just like we did for the wall. Let's get our window area. So and remember, we have 4 windows, so we are just going to take their areas combined, 5.76. Okay, it's even corresponding with what we have here. So the only thing that changed is the U factor. having is 207.36. Watt. Are we correct, or should we calculate over to be sure? Two 207.36 watt. Yes, so that is that for our window. Now for our door, the same thing. We don't have the schedule for the door, so we can assume 2.8. Let's assume it's a Turkish steel door, so I think 2.8 is okay. Now our door area is 1.89 meters squared, 2.8. So I think this is in order, but we can calculate to be sure. So we are having 63.5 rounded up to 64. Okay, it's in order. So now the last thing is our roof. For the roof, yes, I think 2 watt per meter squared Kelvin is okay. We are assuming it's an aluminium roof, and you know, we are going to have sealing or POP, which will also help to reduce the direct conduction. So 2.0 is okay. So let's get the area of our roof. The area of our roof will be, for this conference room, since we are considering this conference room, not for the entire building. So the floor area will be the area we are going to use for our roof. So what's our floor area? Our floor area is 37.13. So 2 times 37.13 times 12. (891.12 watt). Okay, so now that's that for conduction through our building envelope. Now the next thing we're going to consider is the solar irradiance. You know, when the sun shines, there is that particular spot where that receives the most concentration of the sunlight. It shines on the whole surface, but there is that particular point where the sunlight focuses on. So that is what we call irradiance, in contrast to radiance. So radiance is the total focus, is the total incident surface, but the particular spot that receives the most, the direct sunlight, is what we call irradiance. So now when the sun shines, you know, glass can allow, because it's transparent, so it will allow some portion of the light to come into the space. So that is why the glass is considered for this aspect of the heat load calculation. So now, to account for radiation, sun shining directly through the windows, and ventilation and infiltration, this part is going to be a separate part entirely, but let's go with the radiance first. So now, solar heat gain coefficient of our glass, since we are assuming an ordinary clear glass, we are going to assume 0.6 as our solar heat gain coefficient, meaning it will allow 60% of the sun shining on it to come into the conference room. So, and this solar radiation deals with the side the glass is facing. That was why initially I told us to take note of west and north when we were computing the area of our windows, so they will come in handy now. Alright, so this is just explanation, and this is the formula to get the solar irradiance coming through the glass. This here is the definition. Area of window, that is A. E is the solar irradiance, which I explained. Solar heat gain, this is the amount that the sun that the glass allows to come into the conference room, and we are going to use 60%. So now the amount of heat depends heavily on which direction the windows are facing. For example, a window facing west gets much hotter, so because the sun is more brutal on the west side, so that is why this is saying this. So for our solar irradiance, we are going to assume 500 watt per meter squared for the west side, and the standard glass we said 0.6, right? So now, using the above formula, sorry, yes, using the above formula, this is the area of our window, yes, for the solar irradiance 500, well, for this, so this is for the glass facing west. Okay, so now we are not going to use this area. Let's go back to our drawing. So you can see we have only 2 windows facing west, so we are going to take the area for just 2 windows. Now, if you recall, the area for one window was 1.44, so for 2 window will be 2.88. We are going to use 2.88. Since we have only 2 windows facing west. So is there any place I'm supposed to make these changes? Alright, so now I hope you're following. Our solar irradiance for the west side is 500, that's what we are assuming, and we are assuming that the glass is an ordinary clear glass, so it's going to allow 60% of the sunlight to come into the space. So now 2.88 times 500 times 0.6 864 watt. All right. Now this is for the glass facing west, for the windows facing west I mean. For the windows facing north, we also have two windows facing the north, so we are going to use the same 2.88, and the solar irradiance for the north is very minimal. Let's assume 200 watts per meter square, and yes, since they are the same material, so they will allow 60% of this solar irradiance. So we are going to have 345.6. Should we round it or should we just leave it? Let's leave it 345.6. Sometimes too much of this rounding up can even disrupt our work. So now that is that for our solar irradiance, that is the sun shining directly through the glass. Now the next aspect is ventilation and infiltration. Ventilation is when you purposely allow for fresh air to come into the space. You know, maybe when you are having meetings, somebody opens the door to come into the space, into the conference room. Definitely air from outside will come into the conference room, or maybe if there is smoke in the conference room and you want to vent it out, you open the windows and the door to allow the smoke to go out. Like if you remember, I told you air conditioning system do not bring in fresh air, they only cool the fresh air. So if the air in the conference room is having smoke, the air conditioning system cannot remove that smoke. You have to vent it out through opening windows or using extractor fans or opening the doors, whichever way. So that is ventilation. Now infiltration is the same thing with ventilation, but in this case you are not the one purposely allowing the fresh air to come into the space. It's the air itself forcing itself through maybe little gaps under the door or the windows or any gap it might see to come into the conference room. So that is infiltration. So you can see they go hand in hand, they mean the same thing, meaning fresh air coming into the space. So now that fresh air now will of course come in hot, it will carry the outside temperature with it. So now it's left for the air conditioning system to work on it, and that is why we are considering this aspect. So now well, due to time, we are going to call it a day here. We will continue in our next session. Thank you for watching.